This story begins long before people walked the Earth, even before the dinosaurs, before the first signs of life appeared on this planet, before anything existed at all. The Big Bang, the birth of our universe. From this new matter, the first galaxies took shape. Nebulae formed inside the galaxies, and inside the nebulae, the first stars were born. The sun was about to make its appearance in the same way, surrounded by a rotating disk of dust and gas. Gravity pulled the dust particles together, and they turned into huge masses that grew and attracted other masses, future planets. The gases gathered in the sun, which finally lit up. The planets grew thanks to large and small meteorites that rained down from the sky. The energy of each new impact was transformed into heat that gradually warmed up the young planets. Eventually, these became the worlds we know today: Jupiter, Saturn, Mars, and of course, Earth. But what happened to the heat that was accumulated while our planet was being formed? It's still there, hidden in the innermost layers of the Earth's core, and it's constantly reinforced by natural radioactivity. The heat is continually transmitted to other layers before being freed into space. During its journey toward the surface, the heat moves semi-fluid rocks it meets along the way. Like water boiling in a pot, the rocks in each layer rise upward and shed their heat. Then they fall and get heated again. Like huge and very slow cogs in a machine, their movements shift the plates or enormous sheets that make up the thin outer layer of the Earth's crust. In this way, they move whole continents. After 200 million years, this is the result. But the plates are interlocked. That's why, when they shift, the jerky movement along the edges that separate them causes what we call earthquakes. Most of the earthquakes recorded in the world aren't very strong, but sometimes a particularly great one causes destruction and death. Earthquakes also occur at the sea bottom. When that happens, they can sometimes displace the water column and originate waves. These waves are best known by their Japanese name, tsunami, which simply means harbor wave. Regular sea waves caused by the wind are very different from tsunami waves. Let's find out why. Wind blowing over the sea can only move the upper layer of water, forming waves but not affecting movements deeper down. The water particles near the surface move with a circular motion, which helps to propagate the wave along. Deep down, the water particles don't move. The strength with which these waves reach the coastline depends exclusively on the movement in the first few meters of water. A tsunami, on the other hand, can be generated at the bottom of the sea. In case of a strong earthquake, the sea floor abruptly deforms and vertically displaces the overlying water. The entire water column is disturbed by the uplift or subsidence of the sea floor. This sudden movement releases a great impulse of energy, which is transferred to the whole column of water between the surface and the sea floor. In this case, the water deep down moves as well, as deep as 1,000, 2,000, 3,000 meters. Apart from submarine earthquakes, tsunami waves can also be generated by underwater landslides, or when rocks or sediments slide into the sea, by volcanic eruptions, or more rarely, when a meteorite falls into the sea. Alarm systems currently in use in the Pacific and Indian Oceans give advance warning when a tsunami is generated. These systems rely on sensors placed at the sea bottom, which measure variations in the water above and transmit an alarm via floating buoys and satellite link-ups with observation stations on the coast. Once generated, tsunami waves in the open sea travel very, very fast, up to 800 kilometers per hour. They can cover thousands of kilometers and approach coast far from their point of origin with great energy. In the open sea, The waves are rarely over a meter high and are very long, so they're imperceptible. A ship in open sea, for instance, wouldn't notice anything out of the ordinary. The speed of a tsunami wave depends on the depth of the water the wave is traveling through. Approaching the shore, the tsunami's speed diminishes, although it's still much, much faster than an ordinary wave. Also, wave amplitudes will increase dramatically. This is due to the fact that the tsunami's energy flux, which is dependent on both its wave speed and wave height, remains nearly constant. Consequently, as the tsunami's speed diminishes as it travels into shallower water, its height grows. This huge and fast-moving mass of water shifts an entire column of water from the sea floor to the surface. Approaching the coast with a destructive force far superior to any wind-generated wave, it can advance hundreds of meters inland. That's why, even if it isn't very high, a tsunami wave can still cause serious damage along a coastline. When the trough of the wave first reaches the coast, the tsunami appears to make the sea withdraw, often quite consistently, leaving harbors and beaches dry. This can last for several minutes and is a sign to get as far away from the shore as quickly as possible. The crest of the wave will arrive at any minute. It may look like a sudden high tide that keeps getting higher, or a wall of water moving faster than any normal wave. It carries with it the energy of the earthquake, not that of the wind. This is exactly what happened along the coast of Thailand on the morning of December 26, 2004. A tsunami generated by the strongest earthquake of the past 40 years off the island of Sumatra spread death and destruction along the coasts of the Indian Ocean. Images filmed by people who were there help us better understand the devastating effects produced by the huge amounts of energy of the tsunami wave. catastrophic events of these proportions are extremely rare. In the past, the most destructive tsunamis hit the coasts of the Pacific and Indian Oceans. But even the coasts of the Atlantic Ocean and the Mediterranean Sea, to a lesser degree, are at risk and have experienced sometimes destructive tsunamis during the course of history. Studies developed by the Istituto Nazionale di Geofisica e Vulcanologia have documented over 70 more or less destructive tsunamis along the coast of Italy alone over the past 2,000 years. Moreover, destructive tsunamis in the eastern Mediterranean have had a slight impact on the southernmost coasts of the Italian peninsula. An analysis of the catalogue of Italian tsunamis shows that southern Calabria, the Messina Strait, and eastern Sicily have been the areas of Italy's coastline most affected by tsunamis in the past. Some are the result of strong earthquakes, submarine or near the coast. Others have been caused by volcanic activity and submarine landslides. The most famous of them all were the tsunamis that hit Calabria in 1783 and the Messina Strait in 1908. Between 1783 and 1784, Calabria was struck by one of the longest and most violent seismic crises of the past 2,000 years. 5 very strong earthquakes took place between February and March 1783, and some of them caused tsunamis. Recent studies have shown that during this long seismic crisis, there were 10 tsunamis. 7 of them were low intensity, 2 were fairly strong, and 1 was destructive. The destructive tsunami occurred on February 6, 1783, due to a huge portion of Mount Kampala near Scilla suddenly fallen into the sea, about an hour after the first shock. Many people living in the town of Scilla were frightened by the continuing earthquakes and took refuge on the beach at Marina Grande. It was there they were hit by the tsunami, generated by the massive landslide. 3 huge waves crashed onto the beach of Marina Grande. The water was as high as the roofs of the houses, as high as 9 meters, and it spread inland for over 200 meters. The waves also struck the beaches of Chianalea and Marina dell'Oliveto, past the promontory of Scilla. 1,500 people died as a result. The tsunami was seen in other places along the Calabrian coast, from Nicotera to Reggio Calabria. At Messina and Torre del Faro, on the coast of Sicily, the sea went inland for over 200 meters and reached a height of over 6 meters. The earthquake that struck Messina on December 28, 1908, was one of the strongest ever experienced in Italy. The cities of Messina and Reggio Calabria, along with many towns and villages, were completely destroyed and over 60,000 people died. About 10 minutes after the earthquake, a particularly violent and destructive tsunami struck the coasts of Sicily and Calabria around the Messina Strait, causing serious damage and killing hundreds of people. To a greater or lesser degree, the tsunami affected the entire area of the eastern Sicilian coastline, part of the northern coastline, and most of Calabria's Tyrrhenian coast. It started with the sea withdrawal as far as 200 meters. A few minutes later, at least 3 violent waves crashed into the shore. In some places, the first wave was the biggest. In others, it was the second wave. The sea swells lasted for several hours and only gradually diminished. Along the Calabrian coast, the tsunami reached heights of over 13 meters, while along the Sicilian coastline at Giardini Naxos and Sant'Alessio, over 12 meters of run-up was measured. A run-up is the height reached by the water above sea level. Studies of the catalogues of Italian tsunamis have allowed to identify the coasts most prone to this risk. The Istituto Nazionale di Geofisica e Vulcanologia, together with the University of Bologna, is setting up a monitoring network to recognize tsunamis in these areas. At the same time, on an international level, a UNESCO initiative has created working groups of researchers representing different nationalities. Their task is to plan and set up a tsunami warning system for the whole of the Mediterranean. The project is another important contribution towards research aimed at studying and better understanding the Earth, the only planet that's home to life. We need to protect ourselves and to protect the Earth.